Hello everyone, we are Team NUSS SK Power and we are a group of 16 graduate students pursuing Masters in Energy Systems at Northeastern University, and I am Divya, who is the project lead for this project. And our team is divided into three divisions: System Design, which is led by Lokesh, Finance team, which is led by Agustina, and the Development team, which is led by Akshay. We are guided by our Professor Sachin Patel from the Northeastern University and the board members of Northeastern Energy System Society, Anthony, Pavan, Sydney, and Asif. My sincere thanks to all of them. Together, we put together an innovative proposal for our district's use case, North Carolina State University Centennial Campus. The main challenge is to design solar photovoltaic and battery storage system to meet the goals of the university. So let's look at what are the goals. The first goal is to reduce the peak demand to reduce demand charges, and the second goal is to reduce energy usage to reduce overall utility cost, and the third goal is to diversify energy sources to meet the resiliency requirement for the critical loads and also to reduce natural gas consumption. Along with these three primary goals, there are additional goals such as offsetting the greenhouse gas emission and also to get LEED silver certified, and also offsetting the increasing demand of electric vehicles. Together, we are able to address all these goals except the first one, which is the peak demand charges. But why we are not able to do that, which will be covered in the finance section more. Moving on, let's start with our proposal system design. Over to you, Lokesh.
Thank you, Divya. To talk about system design, we were given a Centennial campus in North Carolina. Even though we have many limitations and endorsement parcels, we have designed 9 rooftops, a ground mount, and a floating solar. Firstly, we talk about the rooftop. All the rooftops are designed to maximize the DC capacity by considering enough PA setbacks and considering the racking system with 5 degrees tilt with annual production of 3.1 gigawatt hour and the capacity of 2.47 megawatt DC. The right side graph, you can see the PV production of the buildings and the consumption of energy of the buildings. So let's go to the ground mount. We have designed ground mount by using single axis tracker, and here we have used the racking system of TerraTrack, and the capacity is summed to 2.19 megawatt DC and annual production of 3.8 gigawatt hour annual production. For the floating solar, we have used a tilt of 10 degrees, and we have used the floats of terafloats with capacity of 2 megawatt DC and annual production of 2.8 gigawatt hour. So to design these amazing systems, we have used the panels and inverters. We have used Jinko 540 watt panel and Solar Edge inverter. So North Carolina University has critical loads to support the buildings, which are Toxicology, Partners 3, Engineering Building 2, and Research 1. For these buildings, we have designed 2 batteries. Battery 1 will support Toxicology, Partners 3, and Engineering Building 2. We have used only 1 battery for these 3 buildings because these 3 buildings are nearby each other. And we have used the second battery for the Research 1 because the previous mentioned buildings are really far to the Research 1. To sum everything, we have designed 11 PV systems and a 2 resiliency battery with a capacity of 6.61 megawatt DC, 5.56 megawatt AC, and 1.5 megawatt hour of resiliency battery, which generates 9.375 megawatt hour of annual production, which offsets 10.11% of outage and provides backup of 2 to 3 hours. Thank you. Distribution will continue by Pawan.
Pawan, you're muted.
I believe you're muted.
Sorry for that.
There you go.
Yeah. Thanks, Lokesh, for briefing on the system design. The next part is looking into the interconnection of these systems and also interconnecting them to the grid without any distribution impact. There are 2 major constraints for our interconnection. The first one is no energy can be fed back to the Duke's energy grid, and the next one is the maximum PV penetration on the NCSU grid is limited to 4.3 megawatts AC. Keeping these constraints in mind, we have interconnected all the mentioned systems in 2 different configurations. The first one is behind the meter connection, and the next one is interconnecting the system to NCSU distribution grid. The first topology, behind the meter system, is considered when the minimum load of the system is greater than the maximum PV generation of the PV system. Out of all the systems, there are 6 rooftops which uses this configuration. This configuration is selected for these because it reduces a lot of interconnection costs and also reduces a lot of I square R losses. The second configuration is to interconnect the PV systems with the nearest feeder. This configuration is used when the minimum load of the system is lower than the maximum PV generation of the system. So out of all the other systems, the 5 systems are interconnected based on the priority from the distance from substation. The combined system size of these 5 systems is approximately 5.5 megawatts AC, which is higher than the PV penetration capacity of the distribution grid, which was 4.3 megawatts AC. So we are using the surge microgrid controller, which would allow us to use the same system size without any impact on the grid. Here, surge stands for Consortium for Electrical Reliability Technology Solutions. This controller uses minimal hardware and cost-effective solution for our microgrid. This controller is also tested and demonstrated at the AEC test board. The Surge microgrid controller has 2 main functions. One is monitoring the PV production and also controlling the power flow of the grid using smart inverters and circuit breakers. The operations of this system is using this controller is divided into 3 different categories. First one is on-grid scenario, next is off-grid scenario, day and night. In first scenario, the Surge controller along with the energy management system continuously monitors the PV production, and once the PV production is over 4.3 megawatts, this would curtail the ground mount system production directly to maintain the cumulative production of all the systems under 4.3 megawatts AC. As per our simulation, this curtailment is less than 1% of our PV production. In grid outage scenario, the batteries will kick in order to maintain the resiliency for the critical loads and provide a ride through for them. Only the ground mount and floating solar are equipped with grid forming inverters, and the energy generated would be directly directed towards a specific section of the grid using our energy management system based on the demand and the PV generation at that point of time using the relays and circuit breakers. During the nights, only the batteries will provide resiliency and others would be, and the PV generation would be zero. The finance section will be now continued by Agustina.
Thank you, Pavan. Well, for the financial analysis, we took as inputs in CapEx PV weighted average cost of $1.57 per watt, and for the battery, $450 per kilowatt hour. We'll have 2 federal benefits as MACR's 5-year depreciation and ITC of 30%. For the utility rate, North Carolina is primarily charged with time of use, and when the demand is over 10.5 megawatts, doesn't pay demand charges and is charging only with real-time pricing rate. Calculating this, we achieve a marginal utility rate of 7.4 cents per kilowatt hour, a high energy competitive rate with an escalation of 2.5%. And now, in this case, we are not considering that. So for the financial analysis, we have one on the left is only the 11 PV systems, and on the right, there is analysis for the 11 PV system plus 2 batteries for resiliency. For the first one, we have a PPA of 7.3 cents per kilowatt hour. And for the second case, we have a PPA of 7.9 cents per kilowatt hour, both escalating at 2.5%. In the analysis for the university, for the customer, we have an NPV of discounted at 6.5% positive of $7,000. And for the first case, but for the second case, we have a negative NPV of around $600,000. So going to the conclusions for this analysis, first one, why we are recommending to choose PPA instead of cash purchase. So we did both analyses and the final results are similar. However, we have some conclusions for choosing a PPA. One is financing. The staying an energy fixed rate instead of an upfront cost where it might be difficulties to access them. The second one is operations. North Carolina management is a non-core investment for them and being managed for experienced developer. Also, there could be additional system costs for the developer's margin in case of cash purchase. And in the last one, selling tax credits. They are going to have ITC credits that they have to resell, and they could have like a diminished value through the resale process. And we are recommending a PPA with resiliency battery. So why we should include resiliency battery? Now, in the financial analysis, we only show the investment impact. However, there are equity impacts that the university could face in property and material damage, loss of experiment results, and class interruptions and delays in the schedule. Also impacts in stakeholders way to decrease is going to decrease community satisfaction. So why a battery for peak shaving is not viable in this case? So there are two main conditions that to have a battery for peak shaving. One is demand charge saving, and the second one is a considerable gap between on-peak and off-peak hours from the utility rate charges. In our case, none of them is given. As I explained before, demand above 10.5 megawatts doesn't pay demand charges. And in addition, charges difference between on-peak and off-peak hours are less than 1 cent. That's why our proposal is only battery for residency. Thank you.
Thank you, Augustina. Here is the overview of the development plan. The development plan is being carried out under the jurisdiction of the city of Raleigh. The master plan shown on the right avoids disturbance to future master plan. The rooftop photovoltaic and floating photovoltaic system falls under the office mixed-use zoning designation, whereas the development can start without further review, while the ground mount photovoltaic system falls under a planned development zone. To avoid any mismatches in the required review timeline, the development will be split into 3 phases that will begin concurrently. All 3 systems comply with the applicable codes and standards. We have also analyzed potential risk while planning the project, such as the need to amend the existing planned development zone, which may add significant time for the permitting process. For the ground mount photovoltaic system, we must be aware of the historic land use, so the project team must be prepared to perform any necessary operation pursuant to NC SHPO's review. Furthermore, we have conducted a pre-installation analysis, which include a historical cultural resource analysis, an environmental impact assessment, a topography, climate condition, a web soil survey, and a few more essential studies and surveys. Based on this pre-installation analysis, we formed a permit matrix applicable for all the 3 systems. The construction timeline shown on the right for all the 3 systems is within a 10 to 12-month period based on the permit review and approval timeline. We also have a staging approach in place, which include utilizing shipping container for material staging and temporary storage, limiting on-site inventory to less than 2-week work, using cutting-edge technology like single-axis tracker for maximizing production of the ground mount photovoltaic, and also reduce the disturbance from tree clearance and grading for foundation for ground mount photovoltaic. Finally, we have considered the distribution energy equity impact and have planned community engagement activities, include hands-on training and research opportunity for student, faculty, and staff, as well as workshops and seminar to educate the local community. The project will improve campus resiliency, reduce energy bill, and will promote environmental justice by reducing carbon footprint and mitigate climate change effect. Now, Divya will conclude the proposal.
Yeah, thank you to in summary, we have 6.67 megawatt DC capacity system with annual production of 9.3 gigawatt hours, and we are proposing 2 resiliency batteries with total capacity of 1.5 megawatt hours, which would provide resiliency for 2 to 3 hours. And we are proposing a PPA of 7.9 cents per kilowatt hour, which would assure university to have fixed energy prices over 25 years. And our construction will take about 12 months to build. And once it is built, it will offset about 10% of university's energy consumption. Together with all of this, we also see numerous climate benefits by doing this project, such as reducing the natural gas usage, thereby having offsetting the greenhouse gas emission, which will in turn help the university to become leader in energy and environmental design. So this concludes our overall proposal. And finally, we want to thank all of the judges and then the NREL organizers for giving us this opportunity. Thank you all.